Hi, hello, welcome to first section of chapter 7. In this section, we are going to talk about molecular geometry. I am already excited. I'm really excited to talk about this topic. So let me curb my enthusiasm and focus on this topic. So before we start this topic, so let's take a little bit detour for what do we know about atoms, right? Going back to chapter 1, 2, and chapter 3, the kind of essence where we learned there is that um, electrons are outside of the nucleus and electrons are adjusted in the form of shells and subshells and orbitals to avoid the repulsions between them because electrons are charged subatomic particles and they have this negative charge which makes them repel another electron which has the same negative charge. So it is the whole reason why the shells existed outside of the nucleus, and within the shells, when you have to put, electrons like 2, 8, 18, 32 based on the shell number, you need to create a subshells and orbitals to avoid the repulsions between them. And it is the basis for the molecular geometry as well, because when atoms makes bonds, like we discussed in chapter 6, they were using their valence electrons, right? Again, let me repeat that. When atoms makes bonds by combining with another atom to form a molecule, these atoms are using their valence electrons. So we are talking about now not just one atom electrons, but the electrons of one atom exposed to another atom electrons. So you have bunch of electrons exposed to each other in a molecule, think of Lewis structure, right? In a molecule that they all have same charge and repel each other, which creates a huge issue for molecule. So what is the response of a molecule to that is trying to separate those electronically negatively charged electrons as much as possible. So how do we learn them is under this theory called valence electrons repulsion theory. Now I think you're ready for the content in this section. So molecular shapes can be predicted using the Valence-Shell Electron-Pair Repulsion theory. In short, we call it as VSEPR theory. So VSEPR theory basis is that the negatively charged electrons repel each other. So molecule would try to avoid those repulsions, because molecule wants to enjoy the stability by having its octet electronic configuration. Think of what atom has to go through to achieve the octet number of electrons. Atom has to find another atom, either by bonding a single bond or a double bond or a triple bond. Somehow they manage to get to 8 electrons and feel like noble gas configuration, feel the stability. Just when these electrons started buzzing and creating repulsions between them, then simply atom says, enough is enough, stay away from each other. Just like, how you would put the kids that are fighting between each other, in different rooms, just like that. Molecules will try to separate these electron pair groups as much as possible. When it does, it gives some shape to the molecules, which is what we are going to talk about. So again, let me talk about this with a different perspective. So this is what we know about when oxygen trying to bond with the 2 hydrogens. And here what you see is an oxygen with its 6 valence electrons, which are in blue color here, is trying to bond with hydrogen, which has 1 valence electron each, so that oxygen can have octet number of electrons. But the issue is now oxygen has 8 electrons, which are exposed to each other that are creating repulsions. So to avoid that repulsions, oxygen in water acquired a specific shape to put the bonded electrons between oxygen and hydrogen at one place, and to put bonded electrons between hydrogen and oxygen in another place, and to put the lone pairs of 2 lone pairs of oxygen in separate distance. So it is a problem of oxygen now. And what are we going to study in this particular topic again is how a central atom like oxygen here would distribute its electron pairs in certain distance so that it gets a specific shape. And our goal in this chapter is to know those names of specific shapes and why it is in that particular specific shape and what would be the consequence of it, like bond angles of it. So here is another example. So here a molecule that contains two carbons and oxygen and hydrogen. When you see this molecule, it looks like they have a specific preference to keep its atoms. So what you have here is, let me try to write atoms there to see if I can get a pen, maybe, yes. That's a carbon, carbon connected to hydrogen and hydrogen and a hydrogen. And see that well, they were moving a little bit, but you can see that carbon connected to three hydrogens and a carbon here again. And carbon that I just wrote first is connected to four bonds and it is having its own shape. It wants to avoid bonds one from another so that it can keep everybody happy. And the second carbon also connected to a hydrogen and a hydrogen and an oxygen. So again, the second carbon that is connected to oxygen is also having its own arrangement of bonds so that it can keep its bonded electron pairs away from each other so that that carbon will be stable. And so does this oxygen here. It is connected to a carbon and a hydrogen, and it is also keeping its electron pairs away from each other. So our goal in this chapter is to focus on the central atom in a Lewis structure and see how many lone pairs of electrons present on the central atom and see how it is distributing its pairs of electrons on the central atom so that we can predict the molecular geometry of it. Obviously, there is a little bit more to it. There are little bit sections of it. And again, like I said, at the start of the chapter, this is where you need almost all of your patience here when you learn this topic, and also lots of thinking. All right, let's go through this. As I said before, molecular shape can be predicted by using the VSEPR theory, the Valence-Shell Electron-Pair Repulsion theory. And here is, like broad example of how it would look like. And obviously it's going to get more complicated than this, but here is like, simple way of explaining what is a molecule is and how we start discussing this topic. You can generalize a chemical formula, like a molecule with a central atom that is connected to multiple atoms as ABX type, where A is like a central atom and B is the atoms that are connected to central atom. So central atom can connect to anywhere from 2 to 6 at most, right? We don't have many other elements that connects to more than 6. Even if you do, they were not really covalent molecules, or they were not really non-metals where you need to worry about lots about the molecular geometry. So you just need to worry about a central atom connected to anywhere from 2 to 6. Not much, right? 2, 3, 4, 5, and 6. Again, it's going to get a little bit more complicated in next couple sections here. But for now, generalization. And those you can, generalize those types of, ABX into when B is 2 atoms. You can generalize them into BCl2 or SO2, H2O, or NO2. Okay. And you can generalize them into AB3, where central atom connected to 3 atoms. So those examples you can say like BF3 and H3, ClF3, and SO2 minus. And similarly, you can say that AB4, there are, when central atom connected to 4 atoms, here are the examples of it. And you don't have to remember them. And central atom connected to 5 atoms, these are the few examples of it. When central atom connected to 6 atoms surrounding it, these are the examples of it. Again, you don't have to remember them, and it's not going to be useful for you to remember them because it's complicated. Memory is not going to help you. Only thinking, the process is going to help you. Process by mean is the steps you need to do to identify the molecular geometry. Like you need to draw the Lewis structure, and you need to identify if it has a lone pairs or if it has only single bonds or double bonds. All of these things you need to do, which is why we are going to spend lots of time on this section. This is the most important, I would call it as most challenging section of all of first semester of general chemistry. But if you get it, you're going to be the king in organic chemistry. And so does in this class too. Yeah, I can take you as a king or queen if you get these topics really well. All right. So let's spend a little bit more time on the electron pair groups, right? What I mean when I say here, it's going to get a little bit more complicated here. And what I mean when I say that you don't have to use your memory to remember those molecules is it's going to change depending on if the molecule that you're looking at there has lone pairs or not. No matter how many central atoms it is surrounded by, it actually matters how many lone pairs it has for the molecular geometry. So let's take it slowly, right? So we already discussed here the basis of the VSEPR is that electrons repel each other, right? That's most important news that we need to know how here. So what are those electron pairs? We know that electrons repel each other, and we already know that electrons around an atom, especially in bonds, are found in the form of two pairs, or it can be in the form of lone pair, or it can be in the form of a single bond, or it can be in the form of multiple bonds such as double bonds or triple bonds. All of the electrons in a molecule surrounding an atom is always found in the form of lone pairs. So we are going to identify them as pair of electrons around a central atom, but it is very, very, very important for us to label them as, and also label them correctly as, let me get a correct highlighter, correctly as either lone pairs or single bonds, double bonds, or triple bonds. Especially it is important to label them separately as solely as at least lone pairs and bonds. Should be able to label them as, or at least separate them as lone pairs or bonds, because that's where most things will change for molecular geometry. Let's look into an example, what I mean by correctly identifying electron pair groups as a lone pairs or single bonds or double bonds or triple bonds. Let's look into a fantastic example, set of examples here. Say you have CO2. What it reminds you, what it should remind you is that there is one central atom connected to two atoms around the central atom. So this is kind of like AB2 molecule, right? Don't you agree? AB2, central atom A and two oxygens, so AB2. And your job is to, whenever you look at a molecule from now on, whenever you're going to identify molecular geometry, is focus on central atom connected electron pairs. Central atom currently connected to two electron domains. They were just the two double bonds. And here you label them as one double bond and another double bond. So no matter if you have a single bond or a double bond or a triple bond, I don't want to give that impression to you. That's why I want to clarify that. As you're going to identify the connection between atom into another connection as a single bond or a double bond or a triple bond, but no matter what type of bond it is, you're still going to call it as one set of pair, one set of electron pair. So currently, one carbon is connected to another oxygen with a double bond. Still, you only have one set of pair. So what do you have around the carbon central atom is just two electron domains, only two. So it is kind of perfect AB2. And it is because of two double bonds. Okay, let's look at another variation of an example. What we have here is a ozone. Ozone has also type of structure as AB2 because central atom connected to two other atoms. However, the AB2 that you previously looked at as in CO2 is different from the AB2 that we are currently looking at as in ozone, the current molecule, because we are going to see here 3 electron domains around the central atom. Let's look at what are they. The oxygen has one electron domain with the oxygen on the left, and has another electron domain with the oxygen on the right, and has a third electron domain in the form of lone pair. So the central oxygen atom here has 3 electron domains. Let me highlight that again. That is how you need to identify. You need to identify how many electron domains are there. Electron pairs can be found again around the central atom, is in the form of lone pairs or in the form of bonds. It can be a single bond or a double bond or a triple bond. They were all called as one electron domain or one electron pair. So that's why here we are calling 3 electron domains only, but one is from single bond, one is from double bond, one is from a lone pair. Okay. Do you see why now I'm calling just remembering the formulas isn't going to help you, and also just looking at AB2 isn't going to tell you the entire story, because both the molecules that we're looking at are being called as AB2 type molecules, but they have different electron domains, which means they were going to have a different electronic or molecular structure, which we are going to discuss in a couple of sections. We are just, prepping ourselves. These are just, basics that we are discussing. We are not into real game yet. Let's look into another example. NH3. So NH3 to me looks like an atom, a central atom connected to 3 atoms. So this is an AB3 type molecule. So how many electron domains are around this NH3? If you look for it, again, you need to look for if it has a lone pairs or single bonds or double bonds or triple bonds. So nitrogen has a lone pair there, and a single bond here, another single bond here, another single bond here. So nitrogen, as you can currently guess, has 4 electron domains, and 1 is a lone pair, and 3 of them are from single bonds. Okay, so this is what you have to do before we start discussion of our next topic. This is what I need you to get comfortable with. Whenever you look at a chemical structure, a Lewis structure, you should be able to identify how many electron domains around the central atom, and specifically you need to be able to separate number of lone pairs that is present versus number of bonding types, because presence of the lone pairs is or has the huge change on molecular geometry. Okay, I understand this is going to be lots of information a lot. If you need to pause the video, you can pause the video and rewatch it or digest this, or to summarize all of these again. This is what we did here. I need you to look for electron domains. Electron domains are lone pairs or single bonds or double bonds or triple bonds. Lone pair is 1 electron domain, and either a single bond or a double bond or triple bond are still 1 electron domain. So CO2, we said, has 2 electron domains with no lone pair, but ozone has total of 3 electron domains with 2 from bonding, 1 from lone pair. And we said NH2 molecule has total of 4 electron domains with 3 from bonding and 1 from lone pair. This is what you need to get comfortable with. If you are working with this step, then you are ready for what we are going to do next discussion. All right. So here is where we started kind of going to name the molecular geometry by name. Okay. And here I'm going to introduce you 2 terms to you, which are going to stick with you, which has to be stick with you, those definitions, and you need to understand the difference between those definitions clearly right here. The first one is electron domain geometry. So electron domain geometry is the arrangement of electron domains around the central atom. Electron domains are all of electron domains. It could be a lone pair, a single bond, double bond, or triple bond. All type of electron domains are counted for the electron domain geometry, which is different from molecular geometry, where in the molecular geometry, it is only count the number of atoms that are connected to each other through bonding. Let me repeat that. Molecular geometry is the arrangement of bonded atoms around the central atom. See the difference between electron domain geometry and molecular geometry? In electron domain geometry, you count lone pairs as well as bonds. But in molecular geometry, you only count bonds. So when we name a shape around the central atom, sometimes molecular geometry could be same as electron geometry. Sometimes molecular geometry is different from electron geometry. It is dependent on if the molecule, the central atom, has lone pairs or not. This is something that you always have to check. This is when I say patience. You need to be able to clearly separate the electron domain geometry from the molecular geometry, and only if you are lucky, sometimes it is the same. But there are cases when it is lucky. There are cases when you're lucky and it is the same. There are cases when you are not lucky, when it is not the same, that we are going to discuss exclusively. So here in this slide, we are going to discuss the cases where electron geometry is going to be the same as molecular geometry, because there are some molecules with central atom that does not have any lone pairs. So in those cases, the electron geometry is going to be the same as molecular geometry. So, and I just want to include this sentence here. What is a bond angle? Bond angle is the angles between adjacent bonds, because you're going to see some numbers whenever I show you the structure. So you just need to know what is that mean is. But I'm going to spend some time on discussing the bond angles towards the end of this lecture again. All right. So we are going to look at examples that are going to give the same shape both for electron geometry and molecular geometry in this slide. After this slide, I'm going to show you another set of examples where electron geometry is different from molecular geometry for the molecules that we are studying. Okay, so enjoy while you can of the similar set of names for both the electron geometry and the molecular geometry. Okay, so here is like it is called balloon models because it kind of represents the orbital shapes, like the orbital shapes. So here, what you're looking at is, this is how I need you to look at. You have a central atom in the center. In the center, you have a central atom, and that central atom is connected to two atoms or two electron domains. So when your central atom connected to two electron domains, and if it does not have any lone pair, your molecular geometry should look like that. So your molecular geometry should look like a central atom connected to bonds and bonds like that. Central atom, let me get my laser. The central atom connected to two atoms like that. It is happening because the molecule has no electron pairs. The two electron domains are as a result of bonds, be it be a single bond, double bond, or triple bond. Now, how do we know? This is how we define, this is how we are going to consider, because it is possible to have two atoms connected to a central atom when central atom has no lone pairs. So in this case, your number of electron domains are going to be equal to the molecular domains, and we are going to call this kind of molecular geometry or electron geometry as a linear. It is the name that you have to use to refer when you have a central atom connected to two atoms, and the linear shape looks like a flat. And here is an example that I have a couple models here to show you. Here is the example that you're looking at currently. You have a central atom here. That central atom here, the carbon, that is connected to an oxygen with a double bond, but still this is one electron domain geometry, and it is connected to another oxygen here with another double bond. So this is also another electron-pair domain geometry. Even though it is still a double bond, we still consider it as one electron domain geometry because it is only giving one connection to another atom. So 1 and 2. So as a result, you can see the molecule is flat, right? See, molecule is basically flat. And these two oxygens are 180 degrees away from each other. See, 180 degrees away from each other. So the shape is linear and it has a bond angle of 180 degrees from each other. So you're going to see the examples and you might have to end up learning names about like 15 new names today. They were all different names for different combination of atoms surrounding the central atom. Okay, that's when I guess it gets difficult. Remembering the new names based on how many atoms surrounding the central atom and what are the bond angles. That's where it gets difficult, I would say. Here, just to help your imagination, and also, as I said, what to expect in this chapter is you should be able to understand what does that mean. And this is one shape that I showed you in that slide, what to expect from this chapter. This is the linear shape, central atom connected to two atoms on opposite sides, so shape is linear. Now let's look into a few other categories. I believe I'm going to discuss at least 5 sets of examples here that has the same name for both electron geometry and molecular geometry. So here is the case when your central atom connected to 3 electron domain geometries, 3 electron domains, I shouldn't say geometry. And in this case, when you have same amount of electron pairs and a same amount of molecular domains, then your shape of the molecule is going to be trigonal planar. Trigonal planar. And that trigonal planar looks like this. It is an example, the carbon atom in the center connected to 2 hydrogens at the bottom and another top atom here that connected to. As a result here, the central atom has a shape of trigonal planar. See, can you guys see the shape of planarity now? If I hold it in my hand like this, basically flat. No atom is, out of the plane. They were all on the same plane here. So it is called a trigonal planar. And because it is in the shape of trigonal planar, the bond angles between these bonds, or each bond, is 120. Now, each bond angle has an option to maximize its bond angle, taking the 360 as the available maximum bond angle. So 3 atoms would create separation between each other with the 120 degrees bond angle. So here would be the shape for the trigonal planar. Right now you understand what is that structure is. It is the trigonal shape that is moving around that you're looking at. And let's look at a case where the central atom connected to 4 electron domains, and all 4 of the electron domains are also because of atoms. So let's look into this case when both the electron domains are equal to molecular domains. So you call that name as tetrahedral. This tetrahedral is a new name that you are hearing. Tetrahedral is a name that we give it to molecule or a central atom that is connected to 4 atoms or 4 atom domains to acquire a 3D shape that if you can look here, a 3D shape that has the bond angle between each bond as 109 degrees. It has this pyramidal shape here and a top bond here. So as a result, you call this name as a tetrahedral, which is most popular bond angle that you see in any organic chemistry compounds. Organic chemistry is based on carbon bondings, and carbons popularly form 4 bonds, and there are millions and billions molecules that contains this tetrahedral shape, which is the most popular shape of all shapes in molecular geometry, tetrahedral. Right? Let's look into two more examples. Here, when your central atom connected to 5 electron domains, when these 5 electron domains are also molecular domains, or in other words, atoms, the shape is going to be a trigonal bipyramidal. So what is trigonal bipyramidal is you have one more atom at the bottom here. I kind of don't really have a model for it, trigonal bipyramidal. Let's see if I can create a model. Just give me a second. Well, most of the atom models that we have limits itself with just 4 bonds, so I don't have the perfect model for it. Let's see if you can see it. No. To this trigonal planar, 1 bond at the top and 1 bond at the bottom. So that's trigonal planar. Hope you get it from the structure. So you have 3 bonds in a trigonal planar shape, just like I showed you here, and 1 coming out. Let's see. I showed you this one, right, under trigonal planar. And from this, 1 comes to the top and 1 comes to the bottom of this, which makes a trigonal bipyramidal. That's the name of the molecular geometry. So last case when electron geometry is going to be molecular geometry is when the central atom surrounded by 6 electron domains, and when all of these 6 are atoms, the shape that you call it as octahedral. Octahedral has total of 6 atoms surrounding it, and you have 4 of them in a square planar shape, and 1 coming to the top and 1 coming to the bottom. That gives the octahedral shape. Okay, so this is one set of molecular geometry and electron domain geometry you're going to learn. There are 5 of them, and I'm gonna lead you to the discussion where electron domain molecular geometry is going to be different from electron domain geometry, because I'm going to discuss the cases where the central atom has a lone pair. That is when shape of the molecular geometry is different from electron domain geometry. So treasure these, save these, keep them separate from the next set of examples that I'm going to discuss. Again, this is when I said you need to have the compartmentalization from one topic to another. So you need to distinguish this set from the next set I'm going to discuss. So here we just discussed an examples where electron domain geometry is same as molecular geometry, and we discussed the names of those molecular geometries, and we discussed the bond angles of those molecular geometries. And next, I'm going to take you to the discussion where the electron domain geometry is not going to be the molecular geometry, and here is an example why. So here you're looking at an example, ozone. You know, we previously looked at that 2 slides ago. The central atom here has 3 electron domains. Out of 3, 1 is a lone pair, and see how it would affect the electron domain geometry and molecular geometry. So the electron domain geometry for it would be, you know, because it is surrounded by 3 electron domains, ideally it should be trigonal planar, which is what gives the maximum electron pair separation from one from another. So it should be like trigonal planar with the lone pair on the oxygen and 2 oxygen bonds like this. However, molecular geometry only cares about how many atoms are present, because when you study molecular geometry, you're only trying to tell what is the shape of the bonded atoms to the central atom, not how many electrons present and how did they look like. That's why molecular geometry is different from electron domain geometry. So according to molecular geometry, the shape of this ozone molecule is bent, which is where we focus a lot on whenever you try to identify the shape of the molecule. When somebody says, you know, what is the shape of this molecule, they meant to ask, what is the molecular geometry of the molecule? So this is one of the popular things that you need to remember. There are uses for the electron-domain geometry, especially when you try to identify bond angle, which is electron-domain geometry is going to be pivotal to identify, which has the major say in bond angle of any central atom. But the shape of the molecule is as a result of molecular geometry, because electron pair doesn't have a shape. Electron pair sits on the central atom. That's why it cannot create a shape. Atoms, bonds create shapes, but not the electron pairs. But electron pairs can repel another paired electrons, another single bonds or double bonds or triple bonds. As a result, it can influence the bond angle between electron pairs. So you use the electron pair geometry when you try to predict the bond angle. But whenever somebody asks you to identify molecular geometry, you use how many bonded atoms around the central atom. Okay, let's see. I'm trying to give you some future perspective, and I don't need you to stress out to understand what I'm going to show you now, which is kind of what you would look forward to in organic chemistry. In organic chemistry, what you try to do is you try to make molecules. When you try to make molecules, you need to have the information about the molecular geometry of the molecules that are reacting with each other, so that you could predict what type of product you're going to get. If you know the molecular geometry of the starting material you have, then you can predict what is the molecular geometry of the product. So just an application, just an excuse for you to learn molecular geometry. That's why just before you learn about synthesis in organic chemistry class, they will teach you again these molecular geometries, because unless you know the molecular geometry of the molecules, you cannot correctly predict the product of a molecule. So here is an example where trigonal planar molecule trying to react with a nucleophile to give the product. Here is another example where ammonia kind of molecule with its trigonal pyramidal shape trying to react with another molecule. And here is another example where a tetrahedral molecule being attacked by hydroxide ion OH to form a methanol molecule. So all of these things are going to be major discussions in organic chemistry. And for you to understand what is going on over there, molecular geometry is the clue. You need to understand how many electron pairs around the central atom and what is the shape of the central atom, so that you can correctly predict the shape of the molecule, which is kind of secret to organic chemistry. To be successful in organic chemistry, you need to be really, 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 really comfortable with Lewis structures and molecular geometry and VSEPR theory. If you do that, half the struggle is gone. Okay. All right, here is where we're going to spend major time. This is going to be the most important slide for you to learn remaining molecular geometries of the molecules. Okay, here is the case where electron-domain geometry is not the molecular geometry. Let's look at these examples one by one. Let's see if in a case of there are a total of 3 electron domains surrounding a central atom, but one of them is a lone pair. So in that case, the type of molecule we are going to discuss is AB2, because we are saying there are 3 electron domains, but only 2 atoms. So one of them is lone pair, and there are 2 atoms. So in this case of AB2, the electron domain geometry is called trigonal planar, because electron domain geometry considers how many electron pairs around the central atom. Because there are 3 of them, the geometry should be a trigonal planar. That's when the maximum separation between electron pairs happens. And when it comes to shape of that electron domain geometry, the placement of electrons, you can replace one of the bond with electron pair and show the placement of lone pairs, which is used to predict the molecular geometry. So molecular geometry do not consider the lone pairs when it is predicting the shape of the molecule. So the shape of the molecule is going to be just bent. An example is SO2. What does bent look like? The central atom bent by 2 bonds to the down. Why it looks like bent is because electron pair is not letting these 2 bonds to be in linear shape, like flat shape. If it is not for that lone pair, it should be in linear, right? If there are only 2 atoms. But it is bent because of that lone pair that is sitting on that central atom sulfur. Okay. Let's look at the case of where there are 4 electron domains around the central atom, but one of them is having a lone pair. So in that case, because of the 4, your electron domain geometry should be tetrahedral. But however, type of molecule is only AB3, your molecular geometry is going to be different. So now let's place the lone pairs by replacing one of the bond from electron domain geometry. So let's replace the top bond to have an electron pair there. Now, the placement, because of the placement of electrons, it is easy to predict the molecular geometry, which is trigonal pyramidal. Now it is in the form of trigonal pyramidal, not trigonal planar, even though it has just 3 atoms around it. Trigonal pyramidal. Trigonal pyramidal because, let me get trigonal pyramidal here. I think I have one. If you think of this white ball at the top of the nitrogen is a lone pair doesn't get any shape, right? Because it's not getting any shape, excuse me, you do not count it to identify the molecular geometry. So it is trigonal pyramidal like this. See, it's not flat here. I can still, I can still go underneath it. I can still go underneath it because it's not planar. Because of this lone pair, these bonds cannot be flat. So these bonds cannot have the maximum 120 separation. It must be less than 120 because the lone pair is pushing those bonds away, because lone pair has to have its own space too. Otherwise, it's going to hit the hell out of those single bonds. So AB3 type molecule that contains one lone pair has a tetrahedral electron geometry, but trigonal pyramidal molecular geometry. You understand why I'm saying you need patience, right? There's lots of new information, right? So it takes time for you to digest and spend time, and there is no easy way around it. All of these are something that you need to master, to be successful in this class, and also to have a good understanding about chemistry. Even if you're not going to take any more future chemistry classes, having a knowledge here will make you brighter in other science classes, in maybe biochemistry class or a biology class or a physics class or an anatomy class, or maybe when you are reading a random science article in a newspaper. This information is still highly useful, even if you're not going to take another chemistry class, not just passing this class. All right. Another example, when you have 4 electron domains around a central atom with 2 lone pairs. So in that case, the type of molecule you're dealing with is only AB2 type molecules, but because of the presence of 4 electron domains, the shape of the central atom is going to be electron domain geometry. So because of the lone pairs, if you replace 2 bonds with the lone pairs, it looks like this because of the placement of electrons, which is going to help us to predict the molecular geometry. So molecular geometry for AB2 type molecule with the 2 lone pairs is bent again. Bent looks like this. Why it is bent again? Because it is pushing those 2 bonds to the down, because it needs space for its 2 lone pairs like this. So bent. All right, so we're done with the type of molecules that has 3 electron domains with lone pairs, type of 4 electron domains with the one or 2 lone pairs. Now we are going to focus on central atom that has 5 electron domains. There are 3 examples, I believe, and then we will discuss the central atom that has 6 electron domains with different amount of lone pairs. So let's work on this in this slide. Central atom has 5 electron domains with 1 lone pair. So type of molecule is going to be AB4. Because of the 5 electron domains around the central atom, the electron domain geometry is going to have 5 electron domains. So the shape is going to be trigonal pyramidal because there are 5 of them, right? However, out of 5, one of them is lone pair. So if you replace one of the bond with a lone pair, you're going to have this seesaw shape. Using this, you can predict the molecular geometry as a seesaw-shaped molecule with an example that you can If you draw SF4, it will have this seesaw shape, one flat and two bonds coming out of it. So seesaw shape. So let's look at a few more examples where central atom has a different electron and molecular geometry. So when you have total of 5 electron domains, but 2 of them are lone pairs, the molecule you're going to dealing with is type of AB3 molecules with the 2 lone pairs. But still, because you have 5 electron domains, your electron domain geometry is going to be a trigonal bipyramidal. But if you replace 2 of the bonds with lone pairs, placement of lone pairs looks like this. Now your shape of the molecular geometry is only T-shaped. For an AB3 type molecule with the 2 lone pairs, the shape is T-shaped. And it looks like this, T-shaped. 2 atoms in linear and 1 across. Okay. Another example here, 5 electron domains, but 3 lone pairs. So type of molecule is AB2 that you are dealing with. So electron domain geometry, like the previous 2 examples, still trigonal bipyramidal. But because of the 3 lone pairs, if you replace these electron domains with the lone pairs, you're going to replace all of these 3 trigonal pyramidal bonds. So you have 3 lone pairs, which will help us predicting the molecular geometry, which is linear. So shape would look like this for a molecule called IF2-1. All right. We have 2 more examples. They were based on 6 electron domains. So when you have 6 electron domains, but 1 lone pair, because of the 6 electron domains, you have the actual shape of octahedral for an AB5 molecule. Octahedral, if you replace one of the bond to place a lone pair, so we'll have this shape, which leads us to the molecular geometry shape as a square pyramidal. So square pyramidal is found in a molecule titled BRF5. BRF5 has a square pyramidal shape. You have a square and a 1 bond coming out at the top. Let's look at the last example. Hooray! There are total 6 electron domains, but with the 2 lone pairs. So molecule called AB4. Because of the presence of 6 electron domains, the shape of the molecule is going to be octahedral. So you replace 2 of the bonds with the 2 lone pairs, so square planar. And square planar, because of the placement of the lone pairs, you can easily predict the molecular geometry by removing the lone pairs, which is going to be square planar. That looks like square, flat molecule, but 4 squares. Right. So these are all types of molecular geometries that you have to learn in this chapter. We are only halfway done because we are going to use these for the bond angle, but we did the major work already in this chapter. This is what you need to know in this chapter. You need to know what is the molecular geometry for every possible scenario on central atom. So I would say we discussed, let me go back to previous slide. We discussed 4 in this slide, and we discussed another 4 in this slide. So we discussed total of 8 examples where electron domain geometry is different from molecular geometry, 8 examples to be specific. A couple slides ago, we discussed 5 examples of where when electron geometry is same as molecular geometry. So those 5 plus these 8. So you kind of have to remember total of 18 different electron domain and molecular domain geometries. That's what I said, going to be challenging because everything is a new name to you. There is some familiarity, linear kind of, you can predict trigonal planar, you can predict octahedral, you can predict, but there's some new names like tetrahedral, trigonal bipyramidal, monopyramidal, these names. I understand if you feel like, abrupt about it, but this is kind of what you have to do in this chapter to be successful. This is what you have to do to learn chemistry. This is when people say, chemistry is hard, but I'm trying to do my best here. Again, I'm not calling these topics as easy. I'm the first one to say they were challenging enough. But that's why I try to do all of those extra things for you to make it as easy as possible for you, to help with your imagination, to reduce the stress. So to summarize, our goal in this chapter, Our goal in this particular section is to learn the molecular geometry around the central atom. There are a total of 13 different molecular geometries that you can have, and they were dependent on the electron domains around the central atom and the number of lone pairs as a result. Sometimes electron domain geometry is different from molecular geometry. Nevertheless, electron domain geometry is also very important because when we start discussing bond angles, you only look at electron domain geometries. Okay. Let's move forward and work on one or two problems, then talk about bond angles to wrap up the chapter. Okay. So this is what you have to do to predict a molecular geometry or electron domain geometry. So first things first, you need to draw a correct Lewis structure. Follow the rules that we discussed in chapter 6. We discussed a total of 9 rules. Follow each one of them with the discipline. Again, with the discipline, because discipline is important when you try to draw Lewis structures. Once you draw the correct Lewis structure, your answer in this chapter is based on your presumption that your Lewis structure is correct. If your Lewis structure is wrong, anything that you do in here is going to be useless. That's why please get the Lewis structure right. Once you do that, then count the number of electron domains present around the central atom. And using those total electron domains, you can predict the electron domain geometry using the VSEPR model. Valence electron repulsion shell theory says, if you have 2 electron domains, you should have linear shape. If you have 3 electron domains, you should have trigonal planar shape. If you have 4 electron domains, you should have tetrahedral shape. So it's going to be different, right, for every combination. So you will predict the electron domain geometry. And in step 4, you will replace the bonds with the lone pairs. When in a case of central atom having lone pairs, then only for the remaining bonded atoms, you will predict the molecular geometry. And sometimes it can be same 3 and 4, sometimes it is not. It is dependent on if your central atom has lone pairs or not. If it has lone pairs, it's going to be different. If central atom has lone pairs, your step 3 answer is going to be your step 4 answer, because electron domain geometry will be same as molecular geometry in that case. All right, I got these 2 examples here to just wrap up electron domain geometry and molecular geometry topics before we go on to bond angles. All right, let's look at this example. So this example is asking us to determine the shapes of SO3 and IClO4-. This is the shortest SOB type of problem that requires you to do lots of work, if you know what I mean by SOB. All right, let's do that. Strategy. What is our strategy is going to be? 4 steps that we discussed in previous slide. First, draw the correct Lewis structure, then identify all different types of electron domains, and then predict the electron domain geometry and see if the molecular geometry is different or same by checking the lone pairs. If it is different, predict the molecular geometry as well. All right. So that's going to be our plan. So for that, you need to draw the Lewis structure. I expect you to pause the video right now and predict the shapes of SO3 and IClO4 by yourself, and then check to see if we both got the same answer or not. Okay, it's really important because you just spend almost 1 hour time on learning all of these, and you want to check yourself if you get it right or wrong. If you get it wrong, this is time when you need to go back and rewatch the lecture or contact me. Talk to me in the class so that we can revisit these topics again. So let's practice drawing Lewis structure again. It's been a while. Let's do that. So SO3, according to rules, you need to first check how many valence electrons there. There are 1 sulfur and 3 oxygens. All of them are from group 6. So each one has 6 valence electrons. There are 4 atoms. There are a total of 24 electrons. So between sulfur and oxygen, I want to choose the sulfur as my central atom because sulfur atom is larger compared to oxygen, and sulfur atom can save the day by using its 3D orbitals if it is needed. So I'm going to use the sulfur atom, and I'm going to connect each one of the oxygen to the central atom. Now I'm going to deduct how many electrons that I use for bonding. For 3 bonds, I use 6 electrons. So out of 24, I am going to subtract 6. So it is going to be 18, and 18 over 2 is going to be 9 lone pairs. What I'm going to do with these lone pairs is I'm going to give it to most electronegative elements, or in other words, the elements that are outside, to satisfy them to have the octet rule. So each oxygen has only currently 2 electrons, which means each of them need 6 more. So they require a set of 3 lone pairs each, like that. So now I ran out of my electron pairs, but oxygen has octet, but not the sulfur. Sulfur only has 6. So what I could do is I can change one of the lone pair to a double bond. So I'm going to do this. I'm going to convert a lone pair to a double bond. So my structure would look like that. Okay. Now let me show you the structure we have. So we both have same structure because it doesn't matter how the double bond is shaped. It has sulfur has 1 double bond and 2 oxygens, as for 3. All right. So if you check the formal charges, it should be the overall neutral. I see 2 oxygens with single bonds having each one -1 charge, but sulfur has +2 charge. Overall molecule is neutral. So it's a correct structure. So now what do you have to do in this chapter to predict the shape of the molecule is, first you need to predict how many electron domains surround the central atom. Central atom sulfur has, as you can see, 3 electron domains, 1, 2, 3, right? This is second one. So there are total 3 electron domains. So 3 electron domain shape should be trigonal planar. And if any one of those electron domains around the sulfur is lone pair, I see no, which means the molecular geometry is also going to be the trigonal planar. So electron domain geometry is same as molecular geometry. In this case, so we got lucky. All right, let's look at another problem. ICL4. So ICL4, again, you can draw the Lewis structure of it between iodine and chlorine. They both are from same group. I would choose the iodine as the central atom because it is the larger element, can add more bonds to itself if it is required. Looks like it does require to add more chlorines to itself. If you check, lone pairs, if you check total number of valence electrons, there are 7 in each, 5 atoms, so 35 electrons, and with a negative charge, total of 36 valence electrons. And if you count for chlorines to iodine, if you make bonds and lone pairs, all of that, your central iodine is going to connect to 4 chlorines and have maybe 2 lone pairs. Yes, it has 2 lone pairs. That is the Lewis structure of the ICL4 minus. Now, once you draw this Lewis structure correctly, then you can start working on predicting the shape. So this iodine has, you're going to predict how many electron domains are there. A lone pair, another lone pair, a bond, a bond, a bond, a bond. There are a total of 6 electron domains around the iodine. 2 of them lone pairs, 4 of them are bonds. So 6 electron domains will give a electron domain geometry as octahedral. Okay. Now you're going to predict the molecular geometry by replacing the octahedral with the 2 lone pairs, which will give you the square shape, or you can call it a square planar shape. That is how you're going to do this. It's a practice, and you're going to have to refer to notes a lot until you get really comfortable. I wouldn't be surprised if you have to use notes throughout the semester when you need to find this, which is not a bad thing. You can always still use your notes when you predict until you get really comfortable with it. And once you get really comfortable with it, or once you get really familiar with it, you don't need to use it. But until you do, just use them. Nothing wrong with it. Anything that stress you less is better. If it stress you less to use the notes and refer to them, that's fantastic. Do it. But don't lose your patience, because if you lose your patience, you cannot think. As we discussed, thinking is what we need in this chapter. All right. So far, if you pay attention, we've only discussed central atoms with if we've only discussed atoms with one central atom, not more than one central atom. What if you had more than one central atom? It's actually not a trouble because you're just going to treat each central atom as its own center and still apply the same rules. The molecule here that you're looking at, methanol, is called methanol. It has two central atoms. One is carbon and one is oxygen. What you have to do, you have to look at each central atom differently. If you want to try for carbon, you're going to identify how many electrons domains around the carbon and comment on electron geometry and molecular geometry like that. That carbon has 4 electron domains because it is connected to 4 bonds. All 4 of them also, because of the 4 bonds, it has tetrahedral geometry. Because all 4 of them are also bonds, but none of them are lone pairs, the molecular geometry is also going to be the tetrahedral for 4 electron domains. And for oxygen central atom, it has 4 electron domains. So electron domain geometry is going to be tetrahedral, but molecular geometry is going to be bent because it has 2 lone pairs. Again, thinking, we cannot understate it. If you look at it, what you just do is you try to individually identify the molecular geometry of carbon and molecular geometry of oxygen. You see here, carbon is in tetrahedral shape and oxygen is in bent shape. So even if you have more central atoms, it is not an issue. Molecule will have arranged itself into its own comfortable shape for each center, which is what you need to identify. So far, what we did before I move on to bond angles is, let's summarize. Our goal in this section is to correctly identify the molecular geometry of any molecule so that you could use it for applications such as, the polarity or intermolecular forces in future, or in chemical reactions, in predicting the product in organic chemistry. All of these things, they were really important. These are like fundamentals for you to start the organic chemistry with, right? So we discussed a set of rules where you need to identify electron pairs around the central atom, and based on that, you could predict either electron domain geometry or molecular geometry. And we just applied it on a large molecule like this with containing more than one central atom. So now what we are going to do is we are going to take everything that we learn about electron geometry and molecular geometry and try to identify those bond angles. Remember, in the very first set of slides, I showed you the bond angles for linear as 180, bond angle for trigonal planar as 120, bond angle for tetrahedral as 109, all of those things. That's what we are going to rediscuss again for all of the possible electron domain geometry and molecular geometries. So there are total 13 of them, okay? So this is the whole summary of the list that you need to know the bond angles for, and this is where we are focusing here. This is where we are going to focus here. This is one table that I find really nice table that includes all of the data. So I'm going to split these into 2 so that we can focus on some and look at them in a large structure. So I'm just showing you one whole slide, but I'm going to split them into 2 pictures and discuss one here and some in here. Okay, that's the plan. We are going to go over each one of them. That will almost, done with our lecture. All right. What is a bond angle? A bond angle is a geometrical angle between the adjacent bonds present in electron geometric structure. Okay, that's very important. Read that again. The information that is highlighted color. A bond angle is the geometric angle between adjacent bonds present in an electron geometric structure. It gets confusing here, right? But this is the most important information. You're going to refer to electron geometric structure. And even me saying adjacent bonds is also, I can see, kind of misleading, but it's the most popular way to say it. Adjacent bonds. Let me add another word here. Why take confusion with us? Adjacent bonds and lone pairs. Let's add that word. Adjacent bonds and lone pairs. So A bond angle is the angle that separates the adjacent bonds and lone pairs around a central atom in electron geometric structure. Electron geometric structure is the only one that is going to give you the real answer about the bonds. So I see why it is saying adjacent bonds, because you were only asked to identify the bond angle between bonds. That's why it said. But when you do that, you're going to have to also consider lone pairs. Maybe put that in a bracket, because presence of lone pairs will influence the bond angles between the adjacent bonds. So, but I cannot understate enough. People have this misconception that you can look at the molecular geometric structure and predict the bond angles. You can make a huge mistake if you do that. You can only correctly predict the bond angle if you know the electron geometric structure of a central atom. Because we go back to VSEPR theory, valence electron repulsion theory. The reason why an atom has a shape is because it has to keep its both the lone pairs and bonded electron pairs away from each other. So when it put away from each other, it uses the bond angles. Okay, this is the perfect bond angle where you both are happy, all of you are happy. So central atom would consider its lone pairs of electrons whenever it is distributing electrons around the central atom in different bond angles. So, but you were only asked to predict the bond angle between the bonds, but you have to refer to the electron geometric structure only. I cannot say it enough times. This is the only useful information. Oh, excuse me, that's pen. Let me get the highlighter. Excuse me again. Highlighter. This is where you're going to use to predict the bond angle. It comes from right from here. Okay, right from electron-domain geometry. So what are we discussing here is, here we are discussing what happens when electron-domain geometry has certain number of, let's say, atoms around it. It has some ideal bond angle, but also you will have some issues with the lone pairs and the double bonds, which is called a deviation from bond angles. Let's take a case where you have just two atoms, okay? Just two atoms. Okay, let's take a first case. Your electron-domain geometry is equal to the molecular geometry because you have no lone pairs. In this case, it has a perfect 180 degrees of bond angle, which is what ideally it should be. But however, in cases of the electron-domain geometry having lone pairs, instead of perfectly splitting the bond angle to ideal bond angle, those lone pairs or double bonds will influence the actual bond angles between bonds and deviate it. It's screw the perfect bond angle. So let me just say here, it's not a huge issue now, or even if you take organic chemistry class, for you to go picky on this. We're just discussing it because it's kind of extra information. Even if you are not really good at predicting the deviation from bond angle, I'm okay with it because it's not a huge topic, even if you are in major organic chemistry class. You just need to know the ideal bond angles and don't stress about this deviation from bond angles a lot. If you can get it, it is fine. It is good for you, but if you don't get it, if you're one of those that don't get it, you're totally fine. But I need you to know at least what is the ideal bond angle is, okay? But I'm just going to spend a few minutes what is the deviation of ideal bond angle is. The presence of lone pairs will affect the ideal bond angles because lone pairs may take up more space around the central atom than it should, and also multiple bonds repel much more stronger than single bonds, which pushes the other bonds away. These are the two reasons. Again, I don't want you to stress over this predicting the deviation from ideal bond angles whole lot, which is not really so important like the molecular geometry. You already did the heavy work in this section. So let's go through that list. So when you have 3 electron groups, and I'm looking at this example here now. When you have 3 electron groups, no, let me get an arrow, and no lone pairs, the electron geometry is trigonal planar. So trigonal planar is going to decide the bond angle. So bond angle is going to be 120, and it looks like in this shape. So bond angle is 120, which is based on trigonal electron geometry. But when you have 3 electron groups in the next case, where one of them is lone pair, the shape is going to be only 120 approximate bond angles, but less than 120. This is when I say the bond angle is decided by electron geometry, is because electron geometry is trigonal planar, so bond angle is around 120. See, the molecular geometry is band. So band, you cannot use it to predict 120. That's where it gets confusing to lots of students. They try to use the molecular geometry to predict the bond angle. Let's make sure you're not going to do that. You cannot do that. You cannot use that. Huge cross mark there. Do not use these to predict the bond angle. They were not useful. You're going to use the electron geometries to predict the bond angles. Here is when I said, like, it is least, should be ideally 120, but it's currently less than 120 because of the presence of lone pair that acquires more space. But again, even if you don't get it, don't worry about deviation bond angles. I don't want you to stress out a whole lot because you already had lots on your plate in this chapter. So now, we are going to discuss these examples where you have 4 electron domains. So all 4 of them are tetrahedral, right? Let's group them and try to make them easy. All 4 of them has 4 electron domains. No matter if they have lone pairs of either a 0 or 1 or 2, all 4 of them are going to have the bond angles near 109. Obviously, it's going to get a little bit less than ideal, but all 3 of them has bond angle about 109 degrees. It is because all 3 of them has same electron domain geometry as tetrahedral, tetrahedral, and tetrahedral. All right, let's make sure we are not going to use this to predict the bond angles because they were not useful. So in the case of 5, let's see. Okay, I'm going to group all of them together. So because it's easy, when there are a total of 5 electron domains, all 5 of them has the same electron domain geometry name, trigonal bipyramidal, and all 5 of them is going to have approximately similar bond angles. I guess I see why it's going to be a little bit different here. Let me not summarize them so easily. Let me go back to summarize them as set of 2. Set of 2. So first set, it is working fine because they were having the very much similar bond angles of 120 and 90 and 120 and 90 because you were only adding just one lone pair from first example to second example. It's working fine. But in the next 2 cases, the shape is drastically reduced from having 3 bonds in here. Let me use the highlighter. So here to here, I'm comparing. One of these seesaw bond is taken out. So this bond takes the shape in here to a T shape. In this case, it doesn't need to have them in 120 degrees. It cannot have them in 120 degrees because lone pairs cannot let them allow. So the maximum angle they can have is 90. And in the case of trigonal bipyramidal with 3 lone pairs, so the 3 lone pairs will occupy around central atom like this. So they put the 2 bonds opposite like this, kind of like from here to here, easy to see. You take away this bond that is hanging down here. So bond angle is 180. It's kind of only exception that you can say that doesn't actually fit in the mold. Again, you can see here, you can generalize all 3 of them that has 6 electron domains into one category where you have octahedral, and all 3 of them has same bond angle of 90, 90, and 90. Because not much significant change, because even if you have a bond or lone pair here, either bond or a lone pair, they're still holding in this square planar shape that still has the bond angle around 90 degrees. That's what you need to know about bond angles. Bond angles can be predicted from the electron domain geometries. It is always depending on how many central central, how many electron pairs around the central atom. You could generalize, luckily, most of them. Tetrahedrals, when you have 4 of them, you could generalize. When you have 6 of them, octahedral. When you have 5 of them, it is going to be trigonal bipyramidal. That's the, I guess, trickiest part, where it has variable bond angles whenever you have 5 electron groups around it. So it comes with practice or memory in the case of 5 electron groups. I guess you cannot make it too simple. It's still chemistry after all. How can you make it too simple? All right. Let's discuss the last example I believe, in my opinion, in this lecture. What is the effect, what we just discussed previously, an example of bond angles on deviation. What is the effect of having a presence of lone pairs on the bond angle? If you look at this example and history, think about the bond angle before you look at the answer to see if you should predict that there are 4 electron domains around the nitrogen there. So it should have tetrahedral shape, a bond angle of 109, but because of the lone pair presence, it's currently a little bit less than 109. Still, if you give me 109, I would take it because I don't want you to stress you a whole lot. So if you look at this example here, in this example, you have a total of 5 electron domains around the sulfur, but 1 of them is a lone pair. So as a result, the bond angle screwed from ideal 120 to 101 and 180 to 173. So it changed. Let's look at another example. So fluorine connected to bromine. In this case, bromine has total of 6 electron domains. So octahedral is the shape, and they should have, octahedral is the electron domain shape, and they should have bond angles of 90 between each bonds. Because of the presence of lone pair, it has a less than 90 degrees bond angle. Here is another example where carbon connected to multiple bond and has 3 electron domains. 3 electron domains, the electron geometry is going to be a trigonal planar. So with the 3, ideally it should have 120 degrees bond angle, but currently because of the presence of double bond, it pushes the single bonds area much more farther because double bonds need much more larger space because they repel larger. So it's going to be 122 versus only 116 between single bonds. I believe this is the very last problem. Let's see. In this problem, it is asking us to predict the bond angles for each different central atom and see if any one of the atom bond angle changed from ideal if there are going to be any cases. I see there are going to be cases where bond angle is going to be changed from ideal bond angle. Let's look into them. So for this, first, you need to identify, just like what we did in last slide, you need to identify how many electron domains around each central atom and check if any one of those domains having double bonds or lone pairs, so that you could change the bond angles to lower than what it is ideally should be. So this is what we identified. Carbon has 4 single bonds, so all 4 of them like a plain straightforward electron domains. Next, carbon has a double bonded oxygen, so it has a special deviation kind of type with the 3 total electron domains. And the oxygen that is connected between carbon and hydrogen has a 2 lone pairs and 2 bonds. It also has kind of deviation. This is when, again, you have to think. So now you're going to apply what you learned. The carbon on the left here has 4 electron domains, so it is tetrahedral because all 4 of them, as a result of bonds, shape is still tetrahedral, no change. And carbon here has 3 electron domains, so trigonal planar, so molecular geometry is also trigonal planar. And oxygen here has the electron domain geometry as tetrahedral, but the molecular geometry is going to be bent because there are 2 lone pairs. This is when you need to start thinking deeply, right? Now, for tetrahedral with no lone pairs, you would give the actual bond angle as 109. And for Carbon, the trigonal planar with a double bond, you give a little bit larger bond angle than 120. For single bonds, you give less than 120. And with the oxygen lone pairs, you'll see it has less than ideal tetrahedral bond angle of 109. This is from section 1. I know this is a long lecture because we discuss a whole lot of it. Unless we spend about this much time, you would go nuts, which is my experience tells me that I need to be as thorough as possible. And I added a whole lot of content to this particular section. I spent maybe 5-6 hours or maybe more than that in re-editing all of these slides just before I recorded this lecture, because I felt like it is needed based on my last couple years of experiences of teaching this chapter and re-answering students' questions again and again and again. And I try to change the narrative, and I try to make sure you guys will get it faster and be less stressful. Okay. That's all I got from this section. I hope you guys understood all of them so well. You guys already started seeing the beauty in chemistry, which is what kind of it is, right? It's kind of how we all look different. Atoms looks different, molecules looks different, and it is based on how many bonds it is connected to. So what you're seeing now is the beauty of molecules, how they were different from each other and how they were called. So yeah, that's all from me. I'll see you in the second section of this chapter. Take a break before you watch second section. It's a long lecture. I hope you guys had a good time watching this lecture. Bye for now.